Hi everyone, this is me Rosat, and I'm here to give a presentation about the fetal head ultrasound image segmentation and head circumference measurement using UNET model and ellipse fitting technique. So to begin with the presentation, I would like to give a short introduction about the project. Ultrasound imaging is widely used during the pregnancy for monitoring the growth of the fetal. Fetal biometrics like head circumference and many other are used to are essential for accessing the health of the fetus. Head circumference provides a critical information about the estimating the gestational age and the brain development. Ultrasound, which has a 2D and 2D dimensional, is a standard modality for capturing fetus measurement. So the accurate measurement of this fetus head circumference plays a important role in understanding the fetus growth and check if they are within the clinical expectations or not. To talk about the problem statement, head circumference is currently being measured by the sonographers manually and using the 2D ultrasound image. They freeze a section of the ultrasound image and then measure it. So in the right as well, you can see that how this is getting measured. So this is a manual process. It is time consuming and also requires a significant expertise. There is a tricks of intra and inter observer variability. The manual annotation is not scalable for the large amount of the data sets or the real-time application. So there is a need for an automated and reliable method for segmentation and the fetal head, segmentation of the fetal head and measure the head circumference accurately. Talking about the objectives, the objective of this project is to develop an automated pipeline that accurately segments the fetal health for 2D ultrasound images using UNET model architectures and also measure the head circumference from there. Reduce the intra and inter observer variability and give a consistent model-based approach. Improve the efficiency in the fetal biometrics, minimizing the time and effort required for the manual annotations and evaluate the UNET model using the dissimilarity for the segmentation and use MAE for the head circumference to ensure that this has a clinical reliability. Yeah, you can see that there is input image, its annotations, and the annotation filled with the mask. Sorry, the contour fillings. The architecture of this model goes in this way. This is the input image and its corresponding annotations. We fill the contours and then we do the data augmentation for preventing the overfittings and make the model more generalizable. We train this UNET model and then during the inference, we pass the images and get the predicted marks and do the ellipse fitting to measure the head circumference. This is the training of all approaches that I have used. And model is UNET, and metrics is dice for the segmentation, and MA for the head circumference. I have used the weighted loss of dice, focal loss, and binary cross entropy, with the dice getting the highest amount of the weighted. Data set is publicly available. These are the hyperparameters that I have trained the model upon. You can see that there is a five-fold testing for each of the fold. I have generated a training curve, this shows the consistent result. I have also used the early stopping. Going with the intermediate explainability of the model of what I wanted to check what the model is learning in the process of getting trained. So I have used the GradCAMs for this approach to understand each layering. So this is the epoch zeroth result predicted by the model, and you can see that there is a consistent change during the epoch 66, and they are also seeing the relevant informations, or the model is seeing the more relevant information in order to generate the marks. So this provides us a little bit of confidence of how the model is doing a certain kind of predictions. To talk about the result, and since I have used the fivefold, I have generated the dice scores for this set using dice scores, and they are showing a consistent result over the fivefolds with around 0.95 mean dice and has a consistent MAE as well. So this is the input image. This is the ground truth mark. This is the predicted marks, and this is how the ellipse is getting fitted in order to find out the head circumference. So we can see that the head circumference measurement is here, and the dice code corresponding dice code is here. To go with the coding demo, I'd like to show the coding demo. So I have separated some of the important sections of this code. The model holding the unit model that I have shown here, having the encoder and the decoder architectures along with the skip connection. So this is the unit model where we can define the model itself. These are the predicted marks during the inferences, during the training process. The script has major things like the data set preparations, orderly stopping, GradCAMs, visualizations, loss functions, where the loss functions are dice loss, focal loss, binary cross entropy loss, and they are getting weighted. This is the prepared data sets where I have converted the um, images into NumPy array initially by doing certain kind of the pre-processing, like setting up my initial target size and doing the contour fillings, and then um, what happens is I convert these training images or the test images into a NumPy array so that the model will not get any burden during the training. And this is the data preparation set. After the data preparation set, there is this config file which we can configure in order to set our hyperparameters, or where we want to save some of the generated intermediate results. There are some evaluation parameters that we can set. So this is the entry point of the code where we can define our training processes with training and validation processes. And any other kind of the models like evaluation can be done through evaluate.py, where we can calculate the evaluation parameters um, for the test images from here. So we can just come here and just run the Python trainer.py to run the trainer models, evaluate.py to run the evaluate model, and so on. So the configurations will all be used from here itself. So yeah, that's it from my coding demo. To conclude my presentation, my model has received a good similarity scores of around 0.95 and has an MAE of head circumference around 0.28. And this shows that there is a certain potential for the UNET model in order to do the segmentation for the clinical applications. It uses a different technique like dropout layer skip connection in order to preserve the anatomical or the details or the spatial detail. And the performance still was slightly below the benchmark for my model from the existing literatures right now. It's around 0.98, suggesting that there is more improvement for the model itself. The potential future enhancements include exploring the transformer-based models and exploring the other advanced pre-processing techniques in order to solve the training as well. So yeah, that's it from my end. Thank you everyone for participating.